Great, thank you.
Okay.
So in order to give us a little bit of time for discussion after this, perhaps we can try to get started.
Mhm.
So today we have the pleasure of having another theoretical and applied data science lunch and learn. The speaker for the day is Jiaming Qiu. He is a PhD student in the Department of Statistics at Iowa State University, where he works with Dr. Shangtao Dai and Dr. Jiangwan Zhu. His current interests include functional data analysis and manifold data analysis. Prior to coming to Iowa State, he was at University of Michigan, Ann Arbor, where he got his master's, and Tsinghua University, where he got his bachelor's. So please do stay around after the talk for Q&A. Why don't you go ahead and get started, Jiaming?
Right, thank you. Hello, everyone. Thank you for coming to this talk. And today's talk will be about some nonparametric estimates for densities, especially when you have heterogeneity in the sample sizes. And this work is supervised by Dr. Dai and Dr. Zhu of the Department of Statistics at ISU. And well, again, thank you for coming. So let's get started. So the structure of today's talk will be pretty much in two parts. First part will focus on the methods, its motivation and how we actually do it, and some theoretical properties of it. Then we will apply the proposed method to some real data analysis, which including, for example, the ICU patient's age and some rainfall data. So that's the overall structure. Right. So now we start with the first part. So let's give a motivation example. Let's consider the age at admission distribution of the ICU patients. So we group those, once you have the ICU stay, you'll have the age recorded in the mimic data, which is a quite commonly used data set here. And you'll have the age recorded. And you also have a diagnostic code assigned to the patient. One of it is designated as the primary condition that put this patient in the ICU. And we group those ages by their primary conditions, and we'll have several groups, around 900 groups of the observations. And from the first glance, we shall see there are some differences in the abundance of the observations. For example, you might have some common conditions having observations from 100, a few hundred, or even thousands of those patients. While there are some rarely seen conditions, maybe you have just 10s or 30s or so. For example, in the common diseases, the top left, could you see my cursors hovering around? Anyway.
I can see your cursor, yeah.
Okay, thank you. So for example, this to the top left is the adolescent diabetes, type 1 diabetes. And this one is coronary artery diseases. You have some problem with the blood vessels to supplying oxygen to the heart, so heart attack. And this one is basically you have bleeding in the brain, while this is pneumonitis, which is similar to pneumonia, but not quite so. So those are some commonly seen conditions in the ICUs, intensive care units, where people are really sick. While to the right, there are some not so commonly seen conditions, for example, septicemia, but caused by some bacteria that doesn't like oxygen. That's what's the name, suppose. And rheumatic heart failure is a kind of a heart damage resulting from some infection as well. And also morbid obesity, well, that may be commonly seen, but it seems not so common in the ICU unit. So I guess people don't get so sick just because of obesity. And also this one, the last one is particularly interesting to us. This is the abdominal aortic aneurysm rupture. What that means is you will have the patient will have a localized enlargement in the main artery of the body, and it ruptured. This is a very dangerous condition which can kill people in a moment. However, we don't see that common in ICU units. And according to NHS, I Googled the name and found some resource. For example, the NHS says that is most common in men aged over 65, and is accounted for, and it accounts for more than 1 in 50 of all deaths in such age group. So it's not so rare, but we don't see it that much in the ICUs, supposedly because it kills too quick that people don't even make to the emergency room. So there is an interesting topic to see how will the distribution of age as a characterization of the risk associated with aging be for such kind of rare diseases. Though the practical question is, we can't actually draw a nice distribution estimate for it. For example, the dotted black curves are the traditional KDEs for it. You just do a kernel smoothing, and the result is quite unacceptable. As you can see, there are some bumpies and some, you cannot interpret this, right? So that's the issue. So what we propose is a method to borrow information from the commonly observed ones, as we believe there may be some underlying common land for those commonly seen diseases and those rarely seen diseases. And we might be able to borrow information from the commonly observed one, from those we have more information, and to use it in those conditions that are rarely seen. So that's the question and some idea of what we're going to do. So to formulate that, the data structure I'm more interested in will be a grouped samples. For example, you will have Xij, and for each I, it will be an ID sample from some common density, Pi, where those Pi are drawn from some underlying distribution families. For example, a normal distribution family, but with different means and standard deviations. And our question will be how to draw a density estimation for the unobserved densities, especially for those with smaller sample sizes, as we've seen here. And perhaps further on, try to do some likelihood-based inference with this. Well, the classical approaches, for example, are the KDEs, as we just showed, and some log spline is effectively using qubit spline to approximate the log densities. Those are the classic non-parametric methods, which can be very flexible, but they cannot borrow information among the groups, and sometimes they are too flexible and cannot be interpreted. Well, the parametric method are, for example, for statistic, if you look at the data structure, the first come out to mind might be some linear models, for example, random effect models, if you're just interested in the mean or so, where you can, one-way ANOVA, something like that. You can borrow information across the stresses. But the thing is, in that step, there is a modeling assumption that is vital, where it is an assumption, so you must make a good guesses on the underlying distribution itself. But so we're kind of thinking, is it possible that we combine the good things of those two methods to enjoy the flexibility of non-parametric ones, and also enjoy the information borrowing strengths of the parametrics ones? In other words, we're trying to come up with somehow a distribution family from the data itself, which turns out it's possible. So let me illustrate this example, illustrate this idea with a toy example. So what this is, to the top left, are the randomly generated densities from normal distribution. Per se, I just randomly generate some means and some standard deviations and I plot the densities there. Then I take a log of those densities. And it appears to be more structured compared to the densities. They are just a pointwise log of the density curves. So now, how about consider a functional principal analysis, a principal component analysis, or FPCA? It's pretty much similar to the classic PCAs where you have, but just treating those trajectories, those log densities, as a numeric vector, and instead working with the covariance metrics, doing SVD, you're now doing coherent naive decomposition and using the information you got from the covariance operators. But calculation-wise, it's pretty much similar. So now, doing an FPCA, you will have the result shown as a pointwise mean and the eigenfunctions, so that the log densities can be expressed as the mean plus a linear function, a linear combination of the eigenfunctions, just like in the good old PCA. So now, one thing is, especially this eigenfunction is pretty interesting because it looks surprisingly similar to a linear function and a quadratic function. So if you go back to the normal distribution itself, recall that the sufficient statistics for the normal distribution is exactly x and x squared. In other words, the linear and quadratic functions are the sufficient statistics. Or in other words, if you take a look, take a logarithm of the normal distribution, you will have some constant plus some baseline measures plus a linear combination of a linear and quadratic functions, which is exactly what we have here. In other words, we don't even actually need to know this normal distribution family in the first place. We can reconstruct it from the mean and eigenfunctions of the FPCA results. And extending this idea to a general exponential family, we'll arrive at the proposed method, which is shown in this flow chart. So we started from a branch of training observations, training samples, presumably those with larger sample sizes where NIs are large. Then we can do a pre-smoothing step because functional principal analysis, principal FPCAs will need curves essentially, but it cannot handle in discrete observations. So we need to translate those individual observations to some sort of density curves. So you pre-smooth it. In other words, you just use some KDEs or whichever non-parametric smoother you like to draw some density estimates for it. And here, once you arrive at the densities, that's where the previous toy example starts. You have some densities, and then you take a log. Here, I used a centralized log, which means it's pretty much a Gram-Schmidt process to take out the constant part in the log densities. This is so to ensure the identifiability issue, where later we construct an approximation families. So this is some modification to the toy example. Once you have the log densities, you just do the FPCA or coherent naive decomposition to write your log density as a sum of the mean, and the linear combination of the eigenfunctions phi's. Now here you have two parts. First part will be a fixed part, determined by the underlying distribution family of the data generating mechanism P, the mean and eigenfunctions, and another part of the component scores characterizing the distribution of your densities. There are 2 points of view doing this. You can either view this component scores as an observation to some latent random variables, as if you're doing a hierarchical model, or you can also view this in a Bayesian point of view as some prior put on top of the parameters. So now, with those 2 parts, we can construct an approximation family in an exponential form to the underlying density family, P, whose density will just be in this form, just take an exponential of the linear combinations. And another part, the component score, can be used to construct prior knowledge on the natural parameters eta. So now arriving at this too, we can conduct a likelihood-based inference or estimates. And although this approximation family look like a parametric one, but it's actually data-driven. So we kind of having the good side from parametric and non-parametric combined. So now, for example, you are provided with some other observations, potentially with smaller sample size, this capital N being smaller. You can either use the approximating families to get a maximum likelihood estimate to the natural parameters eta, or you can use also enforce the prior information to arrive at some maximum a posterior estimate to the natural parameter. It's essentially shrinkage your MLE towards the prior mean. So that's the overall idea of our proposed method. So with this in mind, how do we assess the performance? Well, since what we want is some parametric family, or at least look like a parametric family, and we want to do some likelihood-based estimation in the very least. So perhaps a good choice for performance assessment will be information loss. For example, the Kullback-Legberg divergence. This is used because this is tied to the likelihood approaches, as the MLE is basically maximizing the empirical version of this KR divergence, right? So it serves as a goodness of fit of the approximating families. If this were to be small, it means our approximating families, the exponential one we just constructed, will be a good alternative to the underlying one, and we don't even need to assume anything except being exponential. And some notations, for example, you have some MLE to the natural parameters, you just plug it into the approximation family, and you have a plug-in density estimate with the first K components as so. And another thing I want to mention is the information projection. If you're given some density in the actual family, you can project it to the approximating one, where the projection will be the element in the approximating family, pk, minimizing the KL divergence. So it's basically minimizing the information loss. So that's the notation. And it turns out we have a theoretical result for it, which basically means if you use sufficient amount of components or sufficient of K large enough, you can approximate the underlying family as good as you want. Here, this lambda are the eigenvalues of the covariance operators associated with the random densities. You can just treat this as the eigenvalues of the covariance matrix in FPCA. In PCA, it's pretty much the same story. And characterize the variation captured in this in the K's component here. And moreover, if you're provided with sufficient amount of fitting samples, your MLE result can also be consistent in terms of KR divergence. And where this AK, I need to mention a little bit, is basically the ellipsis constant of the functions in the span of those first K eigenfunctions, the first K components. For example, if your eigenfunctions happens to be polynomial basis, so this AK will be asymptotically equivalent to capital K square. So that it's basically as you go into higher frequencies, your eigenfunctions will be more wiggly around, it's being more unsmooth. So this condition is merely asking the number of fittings observation shall be sufficient so that it could compensate the unsmoothness in bringing in by using more and more higher frequency terms. So that's the idea. And in the end, if you're working with some Hilbert-Schmidt operators. In other words, the lambdas being summable, this can go to 0 as k and n go to infinite. So the proof is based on a result from Baron and Shu, which says the density can be approximated by sequences of exponential families, and combine that with some result from SPCA, will give the result, will lead to this theoretical result. And certainly one thing is, this is based on population versions, but for sample versions, we will have a similar result, but some additional assumptions will be necessary. It is basically asking in the pre-smoothing step, the density at the pilot density estimate need to be uniformly good. So, but the result is quite similar. So with this, we can show some simulations results. So it demonstrated with Gaussian mixtures, or more precisely, truncated Gaussian mixtures. In other words, we consider a 3-component Gaussian mixtures truncated on -3 to 3, and we compare this to the proposed method to a branch of nonparametric methods, and we also compare it to EM algorithm, which serves as an oracle. The EM algorithm is specifically designed for this truncated Gaussian families. You can find referencing this Lee and Scott paper. Just one quick remark on the truncation to justify it. Because our method will require a logarithm of the density curves, so it will be, the density need to be at least not so small, so that this truncation is in fact to avoid the log infinite issues in practice. And to the left, there are some typical density curves you might see from this family. For example, you might have 1, 2, 3 modes here. You might have 2 modes as this blue curve. So that's the setup. And now, here's the result. The experiment setup is we randomly generate 50 training samples, or 50 group of samples, each with 50 observations from the Gaussian mixture. And we derive an approximation families and the prior information with the proposed method. Then we generate additional 100 sample group from the same distribution, with the sample sizes varying from 10 to 500. And we compare those proposed methods to some classic approaches, and their mean information loss, computed as mean KR divergence, is used as a criteria, and is compared to the oracle, the EM algorithm, which means smaller, we are doing better. So we repeat the entire process for 500 times from the training generation, and we have the result plotted here. So as you can see, our method and also some other parametric ones are performing rather good when the sample sizes are, the fitting sizes are relatively small, and we're also consistently better than other non-parametric methods until you have a relatively large sample sizes. So that's good, means the information loss is pretty good. And now, another thing to worry about will be the number of components, the capital K. How I choose capital K, actually didn't mention it. We propose to use AIC to choose the number of components to use. In other words, you maximize the likelihood, the log likelihood, and you add a penalty by the number of components you use to it, so that you can balance being, well, you have to represent the data well, and you should not be overfitting if you use, which could be a risk if you're actually using too many components, so that your model being too flexible, right? So to the right panel, it plots out the number of components picked by the AIC criteria as the sample sizes increase. So as you can see, it's not choosing a lot of components, which is good, so that the computation will be efficient. And another thing is, keep in mind, this is a Gaussian mixture with 3 mixture components. So there are A free parameters. In other words, as the sample sizes increases, it unveils more and more underlying complexity or more and more underlying structures of the families, of the true families, while our proposed methods kind of succeeded capturing that and adapt to it by picking more and more component to accommodate for the actual informations. So that's another good thing for that. So in conclusion, the simulation looks pretty good, and we have introduced our methods and the series. So I guess we can talk about a little bit the real data. So let's back to the initial motivating example of the age at admission for the ICU patients. So to the right panels, the red, blue, and green curves are the density estimates drawn by the proposed method. And at first glance, we can see at least it is smoother than the KDEs, so that it will be easier to perceive and looks more reasonable, right? So as I've been talking about information borrowing, I actually want to show you how this information borrowing is enforced in a more straightforward way, which arrive here. There are two layers of information borrowing. The first will be the borrowing typical shapes of the density curves as the mode of variation shows. This mode of variation plots are generated by setting all the natural parameters to 0 and varying the case one. So it's essentially the variation bringing into the approximation family by the case components or the case sufficient statistics. And as we can see here, for the first mode of variation, although there's a little variation here, but you can see it acts as if increases in the risk when for people around 60 to 80s as this bump here, while the second and third can be interpreted as a shift of risk from the older ages to the from the elder ages to the older age, or vice versa, which means this density distribution family, as approximation we just came up with, is somehow interpretable in some sense. So that's the first layer of information borrowing, those typical shapes from the training samples. The second layer of information borrowing will be the prior information on the natural parameters, on the parameters. So the top left one are the shrinkage effect of imposing priors on the natural parameters. The ellipses are the priors, and the triangles are the MLEs. And as we can see, when the sample sizes, the fitting samples is relatively small, sometimes your MLE could be way off, but it can be pulled back into a more reasonable region with a prior. And same, so that's in the natural parameter space. And also, in light of the non-unique parameterization of exponential family, we also consider another way of utilizing those prior information in the moment parameter space. So here, expectation coordinate means we parameterize our approximation family in the moment parameters, effectively the expectation of those sufficient statistic. And note that the conditional expectation of sufficient statistic conditioning on the parameters, the moment parameters, will be exactly the moment parameters itself. So we kind of basically do a somehow regression-like approach, which is called a best linear unbiased predictor of the moment parameters based on the observed sufficient statistics from the training, from the fitting samples to come up with the estimate. Effectively, you can think about it, while the natural parameters, the MAP, pulls the MLE in natural parameter space towards its prior mean. This expectation blurb in the expectation coordinate pulls the MLE, those triangles, into the prior mean, but in a different coordinate system. So they're effectively two different ways of doing this. The reason why we come up with these two ideas basically sometimes because in practice, for example, in MAP, we put a normal prior in the natural parameters, which sometimes might be off because you can have some other shapes and maybe eclipsos is not the best prior to use. So maybe changing a coordinate plan will help the things. So that's the idea of that. So in other words, combining this, we'll have smooth density estimate, and it seems interpretable. So how about the goodness of fit? In other words, the information loss. So we still want to know the information loss. But one question here is we don't have the actual densities observed. If we want to compute the KL divergence, there's one constant part we cannot tackle. So just drop it and we arrive at the cross entropies. Still, there is a true P needed. So how about just using a leave one out scheme, a leave one out cross entropies, where basically you just come up with a density estimate with the J's observation out loud, and then you evaluate that. This is basically an average of the negative log likelihood, and certainly under identical IID assumptions, the expectation of the leave one out cross entropy will be the cross entropy itself. And since we're fixing the underlying truths, this could be an honest reflection of the information loss, right? So with this, we arrive at this table result. And let us just focus on the last two columns. This is the mean information loss computed by the leave one out cross entropies. And how do I do it? I set a threshold. I say, if any condition, any primary diseases will have more than 75 patients in that group, I'll use that as a training sample on which I'll apply platelet estimates and get the density curves, then construct approximating families with the proposed method, and that's the training. Then for all those conditions, for all those diseases that are less than 75 patients in the ICU, I'll use them as a fitting step and use them to evaluate the performance, to evaluate the information loss, and on which I can fit those proposed MLE, MAP, or BLUB. And this versus KDE means how much better the proposed method are compared to a classic KDEs. And the smaller it is, the fewer information loss there will be. So as you can see, the proposed method, along with some other non-parametric methods, are always better than the KDEs, while our methods can be competitive to the flexible non-parametric method of log spline, even there are even there are more observations in the group. So the first two columns are the sizes of the fitting samples, and the N here is how many conditions are there associated with this size. So good information loss. And the last column is for sensitivity, because there might be a question about how sensitive the proposed method is towards the trainings, towards the selection of training samples. So a 5-fold cross-validation is conducted, repeating everything here, and the range is reported. In other words, this is the range of how those mean information loss were perturbed if you alter the training samples. And as it seems, it is looking acceptable, as it's not so sensitive to different training samples. In other words, it kind of suggests we have actually captured some structure in the underlying distribution. So that will be. So in conclusion, we have reasonable densities estimates, smoother and easier to perceive, less information loss, And also the information borrowing is in a clear manner through the prior of knowledge, prior of parameters. So we kind of combine the flexibility of non-parametric methods and the information borrowing and interpretability of the parametric ones. So that's our method. So next, I will show one more example very quickly about the rainfall to illustrate how the proposed method can be used to estimate some interesting quantities deriving from the estimated density functions as Haihe basin rainfall. So this river is a river in the northern China, and there are 200 or so weather stations recording hourly rainfall, and all of them will have more than 30 years of records. So one question is how rare those extreme events would be. For example, how big a rain would you expect in every 10 years, 50 years, or even 100 years? Though one can imagine historical records must be very important in this kind of research. However, one situation is some stations in some location might be newer, so they will have a shorter record. Therefore, to answer this extreme value or extreme event question will be heavily relying on the modeling assumptions. For example, in the classic ways, we'll use a block maximum with GeV, effectively fit a GeV distribution on the observations, and inference is based on that. However, the cons is it's an asymptotic result, and it might suffer in finite sample cases. One more thing is that focuses on the tail, and the bulk part may be bad. When I say bulk part, I mean this part, the majority part of the observations where the densities are higher, in contrary to the tail part, right? So what we do is we use the information, the full record from the longer stations to train our estimate, to come out with approximating families, and we use only 10 years of records from some other stations to mimic a situation as if we are borrowing information from the longer stations, from the older stations, and use it for the newer stations, and to see how things work out. So first, we still want to take a look at information loss. The setup is I randomly select 50 training samples, each using at least 30 years of records to train my estimator with the proposed method. And then I get 100 pieces of 10 years of record from some other stations and use it to fit it and compute the information loss with leave one out cross entropy as described previously. And I repeat the entire training and testing procedure for 10 times. And the plot is shown here. So why I say it will be the bulk part? Because think about how KL divergence actually computed. It will put more weight on where the densities, the underlying density is taking higher value. So it focuses more on the bulk part. So as the plot shown here, the proposed method enjoy smaller information loss and certainly better than the classic method of GeV, meaning that we're doing a better job fitting the bulk part, and even comparable to a gamma fit, which is quite popularly used to fit the bulk distribution of participation data. And certainly the non-parametric methods are quite bad because we only have 10 years of record. So bulk part is good. So how about the more important question of the extreme events? That will be the tail part. But before that, let me provide a short introduction on return level. So it's basically the T-year return level is the level you expected to be exceeded once in time T, in year T. You can view it as a solution to the expectation of number of exceedings being 1 or the expectation of the first exceeding stopping time, tau u here. So basically, once you have a process, random stochastic process, and tau u will be the stopping time, which is the process first exceeding u. So that's this return time. And under some assumptions, stationary or identically distributed, it will be basically the 1 minus 1 over t quantile of the distribution function. So that is how it is estimated. You fit a model, you get an estimated distribution function, and you compute the quantile of it. And the empirical return level will just be the empirical quantile from the observations. Some reference could be found in this 2 textbook. So now the result is this. We follow a similar setup as we did in the information loss, and we're averaging over the stations. So 1 dot here is 1 weather station, and the closer it is to 0, the better performing it is. So as you can see, especially when we are pulling information from the prior on the parameters, the MAP and blood performing quite well as their mean differences being closest to 0 and their spread smallest. This is quite remarkable as we only provide them with 10 years of record, but we ask for 20 or 30 years of return period. And even compared to the GEV, the classic method, our variance is smallest as there are some outliers for the GEVs and pulling this mean error, mean differences out of the plotting range. And one more quick remark will be the gamma fix appears to be underestimating the return level as it focuses too much in the bulk part. So in conclusion, our estimate is doing well in the bulk part and also similarly doing quite well fitting the tail. So I think there's some real potential in this proposed methods. And this will conclude my presentation today. Thank you. Questions, welcome.
So this is Jonathan Smith. I have a question about the climate data, the rainfall.
Yes.
With the climate change, you have the possibility that the last 10 years are seeing much more extremes than in the previous 20. So how do you justify your training based on the full 30-year data when being aware that the first 20 years may not be typical for what is the current situation?
Oh, I see. So
okay, so I think I can answer that question.
Thank you, Dr. Zhu.
Yeah, so we do assume some stationarity in this data set for the last 30 years. And even though it is undisputable that there are some global warming going on in the last century, the last 30 years, the temperature increase has not significantly impacted the precipitation in that area. So there are some tests that's been done there that didn't show a significant increase or decrease of the precipitation over the last 30 years.
Oh, okay, yeah, thank you.
Jiaming, nice talk. I was wondering about, you know, in the first part of the talk, you basically have like one categorical factor that is varying. Is it easy to extend your method to allow other sorts of covariates and more complex, covariates that affect density?
Yes, the question, good question. Thank you, Dr. Tandon. We have been considering that question as well. The current step is, it seems it can only accommodate for categorical variables as grouping variables. You might combining multiple categorical variables, making smaller and smaller groups as long as the pre-smoothers can handle it. However, we're kind of not having a very clear sight of how we can accommodate for continuous variables as groupings. So for example, we have been thinking about using some local likelihood approaches to construct some non-parametric link so that we can construct some totally non-parametric alternative to the GLM, but that's still haven't been really answered yet, but that's maybe a very good potential development.
To Dan's question, I think the main issue lies in the data. So I think one could devise method to handle continuous predictor covariates by, for example, chopping, as Jiaming said, chopping them into small intervals and grouping them. I haven't thought about some actual data structure that will allow us to do this, but that is certainly very interesting. I think that could be done with enough amount of data.
Great, thank you.
Thank you. Any other questions? Well, thank you very much, everybody, for attending the talk today. Thank you, Jiaming, for giving this excellent presentation. We look forward to seeing you next week.
Thank you.
Have a good Thursday, Friday, and the remaining of the weekend.
Yeah, thank you everyone for coming.